So today you took you took quiz 3 in the last session, but I'm not going to review that until Monday. Instead, today I'm going to talk about sorting, which is the topic of lab 8. So we have 2 more sessions before the final exam. There's today and then there's next Monday. Both days have labs. And then the final exam will be on Wednesday at noon in this room. All right, here's the problem. We need to write a function named mySort, which gets a vector of integer and rearranges the items, rearranges the integers in the vector so that they're in increasing order. So let's start in the normal way that we do this. Is we'll write test code, and then we'll develop the solution to the problem after developing the tests first. And I'll just take as a starting point some function that, oh, there's me. We'll just copy some code just to get the declaration of main. And we won't need that. And we'll need these. And as you can see what I'm doing, look at this. I'm testing a hello program. I'm testing a trivial program. See, with all my years of experience and the skill that I have, my ability to program so quickly, I still don't skip this step. And I see students in lab skipping this step. And it's so much simpler if you clear away questions about syntax, your include statements, the main function. If you can just sort of clear those details out by doing these incremental builds, I think that you'll work faster that way, and that's my recommendation again to you. All right. Let's go ahead and implement this function. Or write the test code, sorry. Let's write the test code for this. So we're going to create a vector of int, and we'll push some values into it. Say 8. We'll put 5 values on it. We'll put the small value in slot 4. And a big value in slot 1 or 0. So you can see these values that are in V are not sorted. Like, let's take a look in the comment section here, what that vector looks like. Here's our example: 8, 2, 6, 1, 5. And after doing processing, we want to rearrange these numbers so that the vector looks like this. So the problem, you're clear about the problem, right? We're sorting the vector. Okay. I'll do an incremental build. Oops. Oh, look at that. What's the problem?
You need to include vectors.
Yeah, good, thank you. I didn't have the answer until you said that. That's great. All right. You see, I'm just flying through this, right? I switch pages really quickly. It's something you just got to practice. You know, the more familiar you get with the tools, the faster you can implement your ideas, and you develop a rhythm. And but you need to practice. If you're going on to other computer science courses at here, then probably need to practice more and get very fluid with building code. All right, let's see. Now we call the function mySort. We'll pass in v. And then afterwards, we need to verify that the vector has been sorted. And we'll use assertions. How are we going to do that?
Like assert v1 is 1.
Yeah, that's right. Good. That's how, I think, because the vector is so small, we can just do it like that. If it was a large vector with, say, random values in it, we would need to write a routine that verified that each value was greater than the previous one. All right, so it would be 1, and then 2, and then 5, and then 6, and then 8. 1, 2, 5, 6, 8. 1, 2, 5, 6, 8. There we go. Now this is a special point in our solution to the problem. This is where we have our test code developed, and it fails. But the test code is finished. We've written the test first. This is called test first development. Now the problem is to implement mySort. I mean, the test code is not very extensive, so we could add tests to it. But I think what we'll do is we'll keep it simple at this point. So how do we sort? There's a number of ways to do this. And what I suggested to you last time is that you don't look up a technique and copy it down, but try to figure it out on your own. And I still recommend that, even after listening to this lecture, or maybe you've already looked up a sorting algorithm and looked at it. Try to come up with your own sorting algorithm without referring to any other sources. Just think it through. And it's a good exercise because you're going to need to, assuming that you take other courses or do work that involves developing algorithms, you're going to need practice coming up with algorithms that solve these type of problems. So sorting is just sort of the starting point. It's a basic, simple problem that you can work on to sort of practice that skill of developing algorithms. I think binary search was simpler than sorting, but then sorting would be the next level of difficulty, in my opinion. Well, maybe there's linear search or linear processing, like summing up all the values in a vector. Then there would be binary search, where you're searching for a value in a sorted vector, and then there is sorting the vector, sorting an unsorted vector. That would be my levels of my progression through algorithms. That's a good starting point to go through those sort of 3 problems. But you need to practice those, because you'll be hit with a problem in the future that's more complicated than those 3 simple algorithm problems. So if you haven't spent enough time getting good at coming up with these algorithms, then you'll be struggling later on. All right. So there's a number of different ways of doing this. There's a famous algorithm by a catchy name called bubble sort. that does it. And I don't particularly like bubble sort, and but there's other approaches. There's insertion sort, selection sort. Those are two other named solutions to this problem. And so I'm going to show you what I think is the most intuitive, for me, the most intuitive sort of solution for this problem. So we'll start, so we'll have a loop. So we need to process the vector. So you know we're going to have a loop. So let's range through the values of v using an index I. And I may need to adjust this. Maybe we don't go all the way to the end of the vector. Maybe we don't start in position 0. Maybe we start at position 1. So I'm not sure yet. So we're going to have, I is going to range through the vector. It'll be 8, then it'll be 2, then it'll be 6, and it'll be 1, like that. So if we're not, I don't see, at a minimum, we have to move through the vector. Actually, just moving through the vector in a linear fashion is not good enough. We can't get everything sorted with a single pass through each element. We need 2 passes, or something that's like 2 passes. Maybe not 2 entire passes, but we need a loop, a processing loop inside of the main outer loop. So let's think of it like this. Let's use the outer loop to fill in each position in the vector, starting at position 0, with the ultimate value that needs to go there. So when we start in position 0, we want to end up putting a 1 there. So after our first pass, we want a 1 here. And then we'll move, and what we'll do here is we'll swap the value that's in position 0 with the value that's with the 1 that we find, which is the lowest number so far. So at this point in the first pass, you'll see that we have this position here. The first position, position 0, is now set with the number that needs to go there when we're done. So now at that point, let's work on the second number, the second position. And there's a 2 there. So 1 we leave alone, that's done. But now we're going to focus on swapping 2 with another value that's smaller than 2. The next smallest value, of course, 2 is the next smallest value. So we don't have to do anything. We just say, we have to go through the list and see, oh, 6 is bigger than 2, and 8 is bigger than 2, and 5 is bigger than 2. So 2 is the smallest. That's what goes in position 1. All right, let's keep going with that strategy. So we have 1 is position 0 is set. The value in position 2 is set. But now it's the value in position 3. I'm sorry, position 0, 1, and 2. The value in position 2. That's what we want to determine next. Which is the next smallest value that we want to swap out with what's currently in this position right now. So x, I'm using x to mark where we currently are. Actually, x in the algorithm, x will be I. So as we advance I, do you see what's happening? As we advance I, we take another variable, say j, we take another variable j and use it to look at the remaining, something is wrong there. we use j to look at the remaining values that follow I. So here, you know, 1 and 2, they're set. Position 0 and 1 are done. It's position 3 we're worried about. So what we do is we take j and we say, okay, let's make a record of the smallest of the position of the smallest value that we have currently seen, because we're going to go through the rest of the vector and look for look for smaller values each time. So right now we're going to start in this position, position 2, and we're going to use a third variable k. We're going to say k, the value which is 6, it's at k, is the smallest number that we have looked at so far, because we've only looked at one number. Remember, we're in the inner loop, I is set at 2. And we're going to look at the values in positions 3, 4, and 5. And k is going to be our marker. It's our record of the smallest value in that range, because that's the value at k that we need to swap with the value at I. Just to show you in code what we're doing there. We're declaring a k, we're setting it to I. We're saying, hey, you know, we're going to start at I. I is the, you know, at this point we've only looked at one thing. We've only looked at I. And now what we want to do, and we're going to say, so I is the index of the smallest value we've looked at so far. And j should start at 1 past I. And that's where we're going to start comparing what's at k with what's at j. So if v of j smaller than v of k, remember k marks the position of the smallest value we've seen so far. But if j reaches a new value that's smaller, then we found the position of a smaller number. So we want to move k to that position. Let's take a look at how that works. We move j, we start j at 1 past I, and we look at the value there. Is 8 less than the value at k, 6? No, it's not. So we don't do the swap. Let's move j to the next value. Now j is at the value 5. Is 5 less than the value at k? Yes, it is. Oh, well, that's the new value for k then. Remember, k is the smallest value we've seen in the inner loop. Now we move we move j, but j is past the end. J is now equal to v dot size, so the loop condition is false. So we're done the inner loop. And k is left equal to the index of the next smallest value. So we need to do a swap at this point. Remember, 1 and 2 are unchanged at this point. We need to swap the value at I with the value at k. So when we're done this loop, we will swap the value at I with the value at k. And we'll define swap later. So the value at k is 5, and value at 6 remains the same. The value at I, the value at k is 5, and now the value at I goes into the position K, so that becomes 6. And then we advance I. Let me just fill this out here. So this is 5, 8, and 6. It's hard to do this, isn't it? So here, maybe I'm messing that up. I'm going to leave it like this. All right, so now we have I is here, and then we'll set. We go through the same procedure. Initialize K to that spot, and we'll put J at the next one. And then we compare V of K with V of J. V of J is less than V of K, so we swap. So then we move K to J. Then after that, we increment J, and we're done. And then we swap. So we end up with the final vector. Can you follow that? Does that make sense? For me, it would never ever make sense if I watched somebody do this. I would have to do it myself. So that's the purpose of lab. You need to go to lab or go home and work this out from memory, or come up with your own process to sort the values, and then code it up and test it, make it run. That's what you have to do to attain understanding. I can't imagine anybody understanding this without going through and doing it. All right. So once again, I just moves through the vector until we process the entire vector. The final position of I that we look at is here, by the way. So I, in our loop, is going too far. I should not hit the last position. It should stop. The last value that I should take on is the position that's one before the last position, because otherwise I plus 1 is meaningless. If there was no I plus 1 to go to, J wouldn't make any sense. So we can stop I here. We could probably let it hit v dot size, and it wouldn't malfunction. It's just the inner loop wouldn't run. And so it's actually not a problem. If we left this out, it would just be doing an extra step. You can verify that on your own. If we left this out, the inner loop wouldn't run. We'd end up swapping a value with itself. And that would be not a big deal. Now, we didn't define swap yet. So either we define it as a function, or we just implement it right here. And it takes 3 lines of code. What's your preference? Do you want to implement swap as a function? Or do you want me to insert the 3 lines of code right here to swap the values at I and K? Tell me what you want to do. How many people want to implement a swap function? How many people want to drop the 3 lines of code into place right where it is? Okay, that's the winning one. Swapping the values at I and K. The only way to do it is to define a temporary variable. Let's put what's at I into the temporary variable. Now, slot I, or position I, can get what's at J. Can get what's at K. Now that we copied out of K into I, then we can pull out of our temporary variable and put the value into K. It's like having two cups, you know, and you've got fluid, you've got a liquid in each cup, and you want to change the places of the two fluids. You've got milk in one cup and wine in another cup, and they're in the wrong cups. Right? You put the milk in the wine cup. You want to put the wine in the wine cup now. You've got to have a third cup. You need a temporary holder space to hold the data as you're doing the transfer. All right, we did it. We coded it up. And look, we did the test code. Do you see the simplicity of this test first approach? It's like a lot of the doubt will be erased. All we have to do is run it. And it says all tests passed. We're going to be very confident that we got this right. Look at that. Any questions about this? Now, on the final exam, you need to know this. You need to know how to sort. So you'll need to write a sorting routine.
You need to do it as a function. How will you do it?
Yeah, you need to. I'll ask you to implement it as a function. I won't. I'll ask you to do it as a function. I mean, you could take this and drop it in here. So you could replace this function call with this code. You could do that. But I think it's conceptually easier as a function, isn't it? Because you separate out the test code from the work itself that needs to be done here. So you create the vector here, the test vector, pass it to the sorting function, which rearranges things, and then you verify that things got sorted. And really, we should try to break it, right? Maybe what we can do is create another vector where we try to break our algorithm. Say v2. Let's use negative numbers. See that? It's already sorted. Uses negative numbers. It looks funny, right? Maybe our code doesn't work well with negative values. Let me do it like this. And what we'll do is sort v2 here. And there should be no change. Maybe our code rearranges the vector. Whoops. Maybe the code rearranges the vector when it shouldn't. So this vector is already in sorted order, has negative values in it, has a 0. Maybe our sorting algorithm corrupts an already sorted vector that looks strange like this. Seems okay.
Try if there's a number with the same. They have the same number.
Yeah, let's try that. Let's do that. Let's take, see, this say, put in like two, let's work on this one. Put in 2 1s or put in, say, 2 6s? Which one? What do you think?
Two twos. It doesn't matter.
How about like this? How about that? That's what it should look like. It should be 1 2 2 2 8. That's a good test. Looks like it holds up. Well, we did that pretty fast, right? That's it, I guess. Oh, there was other problems. Let's take a look. A running time of sort. Now, this is an important topic, actually. This is something that the computer science majors are going to get more of in the future. And so we'll just get a little bit of it here. And this has to do with, different algorithms have different efficiencies. Some algorithms are very efficient, and they'll solve a problem quickly compared to another algorithm which may be inefficient. Here, I'll give you an example of an inefficient sorting algorithm. Randomly arrange all of the values in the vector and then test to see if they're in sorted order. And continue doing that until you randomly place everything in a sorted order by chance. That sounds inefficient, doesn't it? How long is it going to take to hit, a random rearrangement that puts everything in sorted order? It'll eventually get there, but it may take a long time. So that's an example of a sorting algorithm that's inefficient. Actually, the algorithm that we're looking at here is inefficient. It takes the amount of time that it takes to run is proportional to the square of elements in the vector. But an efficient algorithm, an efficient sorting algorithm, will complete in time that's proportional to the number of elements in the vector times the log of the number of elements in the vector. And that's a lot faster, actually, because the log of n is small. And n squared is a lot bigger than n times log n. So in this course, we're only looking at we're only concerned about these n squared sorting algorithms, because those are the simple ones, the ones that you could just come up with on your own. But there are some clever algorithms that sort values that actually are much more efficient. And we won't look at those in this class. You'll see those in other classes. So this second exercise has to do with measuring the rate at which the algorithm completes. Let's go ahead and do that. And I have lots of explanation here, which you should read. Let me just check what I'm asking here. It's an awful lot to read in this lab assignment. All sorting algorithms rely on a loop nested within another loop. Even the efficient ones are like that. Or they use recursion. The outer loop runs n times. And for each execution of the outer loop, the inner loop may run n times. This is an example of a loop that runs, the outer loop runs n times. The I ranges from 0 to n. And for each value that I takes on, j ranges between 0 through n. So you see, you have n times you do a loop that does n things. So that's n squared. You're doing n squared operations at the core. In the core logic runs n squared times. And this is a simple loop. But here's a loop that resembles the loop that we just used for our sorting algorithm. I ranges from 0 to n, but in the inner loop, j starts at I and goes to n. So this loop executes, fewer executions of this core logic, because in the other loop, j starts at 0 and goes to n. Here, j starts at I and goes to n. So we're saving some work. But it turns out that even with this sort of thoughtfulness, we still get a running time that's proportional to n squared. And I put the math down here for that. Okay, so I'm not going to go through it now, but you can go through this in the lab or whenever. That demonstrates that the number of times the core logic runs is actually proportional to n squared. So I make the conclusion down here. It's a little bit of a proof in there. And so what I want you to do for the lab in this assignment here, in this exercise, by the way, this thing is called quadratic time. Quadratic time means the time that the algorithm takes to complete is proportional to the size of the problem squared, so n squared. So let's do this. Let's count how many times our inner loop runs, and look at the numbers. So I made a copy, and we have an inner loop. Declare a variable inner loop count, and each time we execute the inner loop, we increment the inner loop count. Let's see, I'm going to do here. Let's plot some of the numbers that we come up with. All right, so we'll do something like the following. We'll have n, and some size for the vector, say 100. And we'll try another one that has, say, 1,000 entries in it, and then maybe 10,000. So n will be getting larger, and this is the number of times the inner loop runs. The inner loop count. So what are these numbers? Maybe 10,000 is too big. What's 10,000 squared? Well, maybe it's okay. All right, so for my sort, let's return that value. Actually, that's called a long. Now, I didn't want to, the loop count may get large, so I declared it as a long rather than an int. See this? How many bytes in a long? How many bytes in an int? Anybody know? 4 bytes for an int. So a long would have, how many do you think? Take a guess. If an int has 4 bytes, how many bytes are in a long int?
8.
8, good. Good guess. Doubling. It's actually supposed to be machine independent, but in practice, that's normally how you would think of the size of an int and a long. All right. So now we need to create vectors that are no, that's right. See, we'll need to create vectors that are those sizes. So here we create a vector v. And we're going to have 100 numbers in it. Shouldn't be first, should be 4, I know. And let's put a random value onto the vector. Rand returns a random integer. And let's seed the random number generator too, just to make sure that every time we run it, we get a different value. Actually, let's not seed it, or we will seed it. Let's seed it with the same value 0. So we get exactly the same number each time we run it. And then we'll take a look at what kind of differences we might get when we change the seed. So here we're pushing a random value onto the vector v. Then we sort it, and then we print out what mySort returns. What does mySort return? That's the number of times the inner loop runs, number of times we execute the core logic. And the thing that runs over and over again is this conditional. This assignment happens less often than this conditional. It's this conditional. That's the weak point, the hotspot. That's the expression that's evaluated at every iteration of the inner loop. That's the thing that we're counting, how many times we execute that comparison. So we're passing in, we're creating a vector with 100 values, sorting it, and then printing out the number of times our core logic runs. Whoops, wrong one. Oh. Forgot to return inner loop count. Oops, messed it up. Thought I was in Windows. Got lucky there. The word started with an I.
It needs the end and returns.
What's that?
It needs the end and return.
Oh, it needs the end too. Oh my gosh. Yeah, look at that. It got the end right there. The I made me go, I'm in VI, so I put me in insert mode. It was just lucky the word started with an I. Okay. Let's try. Let's run it.
Wait,
What?
You did that example on
Thank you. Should be the same every time we run it, right? Because we use the same seed, okay? When we change the seed, let's just be clear about what's going on here. Let's make the seed a 1. Should get a different number. Right? Oh, it's the same number. What's that? Wait a minute, it's the size, it depends on, this algorithm depends on the size of the vector. So this C doesn't matter at all. We do exactly the same, because do you remember how we did the algorithm? We do the same scanning no matter what values we look at. We always look at everything. So we don't look for opportunities to exit early. So actually I was just looking at bubble sort actually before I came in here, and there's this little trick you do inside bubble sort to stop sorting as soon as you discover everything's in order, and then you can get variations between different runs of random values. But here the random number generator is not going to have any effect on us. We'll get exactly the same number of executions of the inner loop. All right. So let's take the number. It's 4950. That's how many iterations of the inner loop occur when we're sorting 100 values. I didn't pay attention. Did I get the number right? 4590. 4950. All right, what about 1,000 values? 1,000 random values. $499,500. You know, I don't know if 10,000 is even going to work. We'll try it. Oh, of course it'll work. Let's see, is it going to be slow or is it going to run fast? That's pretty fast. That's pretty fast. 10,000 random values, and the inner loop runs that many times. Oh, the numbers look really similar there, don't they? Yeah, I remember the last time I got these funny numbers just like that. This is just, the nines are expanding here. Can we do 100,000? And if we do 100,000, do we get 499995000? Is that right? Huh?
One more zero.
One more zero?
Yeah, zeros.
I need another zero. Like that? Yeah. So that's like I went from 1 to 2 to 3 to 4, right? And then I need a 5 in there. Thank you. A 5. And let me see. I'll put it right in like that. Did I get that? So this is 2 zeros and 2 nines, 3 zeros and 3 nines. This is 4 zeros and 4 nines. But what happens if the system goes to sleep on us here? Oh, I didn't change it?
Yeah,
Oh, down here. There it is, 100,000. I don't think it's going to terminate. Okay. Time to get a coffee. See, it's squared, right? So it's blowing up. It's blowing up on us. It would be nice to know if the number turned out to be, like that. Sure looks like that, doesn't it? We'd have to do, so the math majors, you can go after this. My interest goes this far, to start looking at that, do the what do they call it? Number theory, right? Would you call that number theory to analyze this? Yeah. Oh, it worked. And look, we guessed it. And it didn't take as long as I thought. All right. So that was satisfying. And let's go ahead and take this scatter plot generator here. And we'll probably crash it with those numbers. Comma separated X data values. Let's try that. 100, 1,000, 10,000. That's 100, and then 1, 2, 3 zeros. So it's 100,000. Comma separated Y values. 4950. Did I get that right? It's 4949. I get these. I can remember these. So it's 49955. Just 1 5. I got it right. Okay. And then it's 4999500. Is that right? It looks too big here. 4, and then we got 4 9s. Did we really do that? Oh my God. All right. It's going to break it. I don't think I. Let's see how smart it is. That's it. It blows up, right? It's not very interesting, is it? Not interesting at all. It's hard to see it. It's hard to see it. It's quadratic. So it's like, you know, it's some function of n squared. We'll have to make the numbers smaller. Like, suppose we did, let's do it like this. Let's try 100, 200, 300, and 400. $200, 19900. Oops, that's the data. $4950. I had it right there for me. And then 19900, comma. I'll try 300. 44850. 44850. Doesn't seem big enough to me. And then 400. 79800. 79800. That's it. Well, it's not a straight line. And it is, in fact, a quadratic. So for the lab, I want you to, you know, like print this or something like that. Like something like this. So you would save the image. And, you know, just save it to, save it into the lab. And commit that with your work, okay? Oh, yeah, here we go. So we want 2 programs. Let me explain this problem. So this is problem 3. So we have here that's 100,000, right? And that looked like it was getting close to not terminating. Let's put in 200,000. And let's build that. I'm going to build it over here. All right, there. That's what we have. So I want to build this program. This sorts a vector with 200,000 random integers. I'll compile it, and then I'll sort it. All right, let's just let that run. Now, let's copy the source code and call this example 3 fast. So example 3 slow that we're now running is an example of a slow sort routine, which is the routine that we ran. See, it's still running, okay? 200,000, a vector with 200,000 random integers. It's still sorting. And now we're going to compare that with a program, a sort routine that runs in n log n time, as opposed to n squared time. So what we'll do is we're going to call the sort routine of the standard library. It's in a header called algorithm, I think. I'm going to just try to remember this here. And so we're going to call sort. I think it's from that header. Okay, I think that's defined. It's a void, so we can't. All right, so we're going to sort it, and then when sort returns, we'll print done. Oh, look, this one finished. That's not too bad. Now let's look at this. Oh, sort. What is the, is sort a part of the vector class? Let me try that. Oh, sorry, I didn't have a semicolon there. The template function requires 3 arguments. Only one was provided, and we need to pass in an iterator. Maybe vector has a sort routine in it. Let me try that. v.sort. Does that exist in the vector class? Let's try that. That's easier than passing in the iterator. No member value. All right. All right, so let's do it like this. V dot first, V dot end. Those are iterators. So we want to sort V between the range that's defined by the first and the one past the end. Let's see if that runs. All right, no member name first. another word I can think of.
You just do B0.
No, it's got to be what's called an iterator, a vector iterator. So it's, is it front? I think it might be front. I'm not reading the manual here, so, all right, I gotta look it up here. I don't want to give up. Oh, I know, I remember. It's begin. There we go. It still doesn't work. What is the problem? Two arguments with three are provided. Hold on there. Can't read that. No matching function called a sort. Oh, well, there is no sort.
Isn't it my sort?
No, it's not the code that we ran. It's what's the C++ sort algorithms? It's oh. We don't pass. We just pass it in like this. Finally worked. Look, do you see that? Look at that. And that's amazing. Now watch this. It just goes to sleep. See the difference between an efficient sorting algorithm and an inefficient algorithm? It makes a big difference. And, you know, if we just add another, this actually, we saw that this completes 200,000. But if we put it at 300,000, it probably wouldn't complete by today. It'll just run. Who knows, at some point it's going to run the rest of our lifetimes and add it together even. So that's what happens. You really get these behaviors where running times blow up if you design the algorithm wrong. Another thing that's very interesting is that there are some problems that don't have efficient algorithms. And a famous problem is called the traveling salesman problem. And you've got, say, n number of destinations the salesman has to go to. And there's a distance from each city to the next is known. And so you want to devise a plan so that the salesman visits each city once, but minimizes the total travel distance. That's a hard problem. There's no efficient algorithm for that. That gives you the optimal solution. The optimal solution exists, but when the number of cities gets large, it can't be computed. Because, I mean, it could be computed with a theoretically fast computer that runs a theoretically long time. You can always theorize about a machine that would complete. You can prove that such a machine would complete in a certain amount of time, but it couldn't be done with physical computers as we have them now. So one of the areas where researchers are looking for breakthroughs is called quantum computing. So, you know, in quantum physics, there's a lot of strange phenomena that happens at the quantum level. And so people are hoping that if you can perform computing tasks at that level, that you're going to be able to sort of have breakthroughs on these hard problems like the traveling salesman problem. So that's that's a current area of research, and we completed here. And anyway, we're not going to get into that here. Just thought I'd mention it. That completes the lab, by the way. And you may want to make a note of how I called the the sort routine here. I needed to include the algorithm header,
Website.
and I had to pass it in like this. Yeah, I should add it to the website.
I think it is.
It is? I had it there? Oh, look at that. All right.